It's already 2:02. I think we can start. So I'm glad to have invited Professor Wang and his PhD student, Dr. Fenglei Fan, to give us a seminar on AI interpretability. Professor Wang is the director of Biomedical Imaging Center in Rensselaer Polytechnic Institute. I believe many of us already knew him, so he's well known for his research and expertise in the field of CT image reconstruction, from earlier spiral CT reconstruction to iterative CT reconstruction, and now there's deep learning methods. So he published many papers, like maybe more than 500, and he's also a fellow of many societies like IEEE, SPIE, AAPM, OSA, and so on. And Dr. Fenglei Fan is a PhD student from Professor Wang's group within the Biomedical Engineering Department. He's also an IBM AI Horizon Network Fellow. So his research work is focused on deep network design, analysis, and applications. So, so without much delay, let me give the microphone to the speakers. So.
Okay, thank you for your introduction. Sure. Okay, let's get it started. Okay, hello everyone. My name is Fenglei Fan. Today, my advisor, Dr. Ji Wang, and I would like to discuss with you about the interpretability of deep neural networks. So this presentation will be based on our previously published survey paper. Deep learning interpretability has been a hot topic recently because interpretability is an essential issue. This issue is very much cared by a lot of people. No matter you are doing the application study or the methodological study, I guess the interpretability will be useful for your research. Here we show the trend of interpretability research by plotting the number of articles with respect to the year of publications. Clearly, we can see from this plot that in the past years, the number of articles increases exponentially. So this field has a huge momentum. What's the meaning of interpretability? Although people discuss the interpretability a lot, I guess the meanings of interpretability are still vague to us. Here, the paper by Lipton provides an illustration on the meanings of interpretability. This paper divides the interpretability into three aspects. The first aspect is simulatability, which is to understand the whole model. So what is the whole model doing on the top level? In terms of simulatability, there is a good paper published in the last 90 in Science. So this paper finds that there is a connection between a radio basis function network and the interpolation problem. They find that the selection of radio basis function in the radio basis function network is controlled by the regularization term of the interpolation problem. The second aspect is decomposability. This is to understand the whole model by understanding the components of the model. This is kind of like the engineering. This is kind of like the modularized idea. The modularized idea is widely applied in the engineering field, especially in the system design. This is kind of like a divide and conquer. To understand the whole system, we divide this system into many parts, and we understand this. We try to understand the functionality of each part, and then collectively we can have a good understanding for the whole model. The last aspect is transparency. This is to understand the training process. What makes the interpretability a difficult job? We summarize 4 barriers. The first barrier is human limitation. The expertise is often insufficient in many applications. For example, some people use deep learning to predict the weather. However, we know that the weather prediction is a kind of the butterfly effect. Even our human do not have a good understanding for the weather prediction problem. How can we expect the deep learning model to have a good illustration? The second barrier is the commercial. Commercial barrier. A company profits from black box models. If a model is a black box, it can prevent this model from being reverse engineered. Also, if a company would like to offer interpretability, it means an extra cost to do. The third barrier is data wildness. The available data are often in high-dimensional space and are often heterogeneous. The high dimensionality and heterogeneity of the data is a trouble for interpretability. The last barrier is the algorithm itself. A deep learning model is a highly nonlinear model, which involves a lot of nonlinear operations, such as dropout, batch normalization, and so on. Currently, we do not have sufficiently powerful mathematical tools to understand the nonlinearity. So also for some types of neural networks, such as recursive neural network, the chaotic phenomenon may happen, which makes the whole system intractable. So now let's get started to review interpretation methods. We'll go based on this taxonomy. This is from our survey paper. In this taxonomy, we divide the interpretation methods into two categories. In the first category, post hoc interpretability analysis. This category can be further divided into 7 classes: feature analysis, model inspection, saliency, proxy, advanced mathematical and physical analysis, explaining by case, explaining by text. The second category, ad hoc interpretable modeling. This category can be further divided into 2 classes, interpretable representation and model renovation. Let's check out them one by one. First, feature analysis. Feature analysis methods are centered in visualizing, comparing and analyzing the features generated by neurons and layers. Through feature analysis, what sensitive features are and how these sensitive features are processed by a neural network can be identified, in which we can understand the rationale of a neural network well. Image inverting is one representative method in feature analysis class. We know there is information loss when a neural network processes an image. However, we do not know what kind of information is lost by the neural network. So here the image inverting is address this issue. So image inverting method construct an image that can copy the features of the original image as much as possible. So by comparing the constructed image and the original image, so we can know what kind of information is lost by the neural network. So for example, in the right figure, the top left is the original image, and the rest 5 are reconstructed images by the features of 5 different layers. So based on this result, we can see that the information of the building profile is still retained, but some other information, like the color information, like the human information, is lost. The second method, activation maximization. Activation maximization is to generate an input image that can maximize the output activation of a neural network. So this method is also called deep dream because it can generate the most desirable image for a neural network. So basically, to generate a deep dream, we need to update the input with the help of the we need to update the input so that the loss is minimized. So by analyzing what a deep dream look like, we will know what kind of features are preferred by a neural network. Lastly, neural dissection. So neural dissection is to compute the receptive field of a neuron. Then we analyze what contents are appearing in receptive field of a neuron and their appearing frequency. So based on that, we can interpret the role of a neuron. For example, in the right figure, we notice that some units are always focused on the snow part of the image, while other units focus on the other part, such as the mountain top. So analyzing the receptive field of a neuron can help us understand the functionality of a neuron. Now we come to the second class, model inspection. So model inspection method use external algorithm to dive into a neural network, which is a systematic way to extract information. Influence function is a representative method in this class. Influence function addresses the question, how will the model's loss change without a given training point? So give a test image and a model. The model will have a loss on the test image. So suppose we remove a given training point from the training data set. Let us check how the loss will change, how the loss on the test image will change. If the loss increases, it means the removed training point is useful for the predictions of the test image. But if the loss decreases, it means the removed training point is harmful for the predictions of the test image. So basically, influence function can identify which in the dataset is harmful for the prediction of the test image. The second example is important data path. Important data path can tell us what is the important data routing path in a network. So the idea is straightforward. We block some neurons in every layer collectively and check the network performance. If the network performance drops a lot, it means the blocked neurons are important nodes. As a result, the paths formed by these important nodes are important paths. So in this way, we can identify the important data routing path in a network. So now we come to the saliency class. Saliency class currently, saliency class is to identify which attribute or which part of the image is most relevant to the model's prediction. Currently, saliency class is a dominant interpretability method in this field. Saliency map is also very useful. For example, given a polar bear, a model can classify this polar bear into the polar bear class. However, we know that a polar bear is often appearing with the snow or ice. So how can we know if a model takes advantage of the features from a polar bear or the features from a snow to make a decision? But with the saliency map, this problem can be resolved. We can check the saliency map to see if the neural network takes advantages of the correct features. Currently, there are many ways to derive a saliency map. Gradient-based method, mutual information, layer relevance propagation, and class activation map. So the gradient-based and mutual information-based are kind of straightforward. So we focus on the last two. Relevance backpropagation. So in this method, so we first define the relevance scores for each layer. Then we decompose the model's prediction as the sum of the relevant scores in each layer. Then we compute the relevant scores in the last layer. Next, we backpropagate the relevant scores in the last layer to the earlier layer until we arrive at the input layer. So the relevant scores in the input layer can give us a heat map. So we can have we can analyze this heat map. Then the class activation map. So this is also a classical method to generate saliency map. So the class activation map is also called CAM. CAM is to identify which part of the image activates the class most. So given an image and a model, the model will return a class to the image. Suppose we take all the feature maps of the last convolutional layers and weight each channel by the gradient of the class. We can generate a heat map, and this heat map can tell us which part of the image activates the class most. Now we come to the proxy class. So proxy method prototype a more interpretable model that can mimic the original black box model. To prototype a proxy, we can directly do the rule extraction. We can extract rules from a neural network. So given a data set, after we train a neural network on this data set, we can check the parameters of this neural network. And then we can construct a rule system based on the parameters of a network. We hope that the constructed rule system is functionally equivalent to the original network. Usually we can do that. So apparently the constructed rule system is more interpretable than the original network. So in this way, we can gain the interpretability. The second way to get the proxy is knowledge distillation. The idea here is to train a student interpretable model from a teacher network based on the predictions of the teacher network. The predictions of a teacher network is also called soft labels. Soft labels are more informative than the one-hot labels because soft labels can provide relatively different likelihood for different classes. For example, a cat is more likely to be classified into dog class instead of a mountain class. But in terms of one-hot labeling, both the dog class and the mountain class has a probability of 0. But in contrast, the soft labels can provide the different likelihood for the dog class and the mountain class. So this is also why the student model can inherit the generalization ability of the teacher network. So for the selection of the student model, we can choose models like a decision tree or the rule system or the rule set. These models are more interpretable than the neural network, so that we can have enhanced interpretability. The second method, local explainer, can also work as the proxy, but it is a local proxy. So the idea is that the model can be complicated, but a model becomes simpler when examined locally. So the local explainer is to approximate the original model in a local space. So the procedure to construct a local explainer is that given a sample, we can synthesize its neighbors, and then we compute the predictions of neighbors. Finally, we fit neighbors by a linear classifier. So the resultant linear classifier can approximate the original model around the given sample. And then we can analyze the resultant linear classifier to get the importance of the attributes of the given sample. Next is the advanced mathematical and physical analysis. So the methods in this class put a neural network into a theoretical, mathematical, or physical framework. So in the framework, the network can be better understood in light of mathematical and physical knowledge. For example, the differential equation. So this example is from the paper, which is 2018 neural Reef's best paper. So the authors in this paper established a connection between the ResNet and the ordinary differential equation. They found that by adding more layers and taking smaller steps, the ResNet becomes the discretized version of ordinary differential equation. Then they argue that why not directly why not directly define the layer-to-layer relationship by the ordinary differential equation. So with this idea, they get a model called a neural ordinary differential equation, ODE-net. So in the right figure, we can see that the fitting result by the ODE-net is more smooth and more continuous compared to that of a residue network. Theoretical deep learning is also useful for interpretability. Currently, theoretical deep learning mainly investigated three issues: representation ability of a neural network. For example, why deep networks work better than shallow ones? Why networks with shortcuts work better than without shortcuts? The non-convex optimization, the good local minimum problem, also the generalization ability. Recently, generalization ability is a very hot topic because some researchers find that the generalization of a neural network follows the double descent curve, which challenges the traditional view. Traditionally, people believe that as the model complexity increases, the model will become overfitting. However, recently people find that for a deep learning model, as the model complexity increases, the test error will first go down, then goes up, but eventually the test error will go down to reach a very low level. So this is a very interesting phenomenon. So in the future, we hope that the advances of theoretical deep learning can provide us good insight on interpretability. Now the class explaining by case. Explaining by case is a case-based explanation. So the idea is that people understand the example. So for example, given a product, we may not be engaged by the statistical numbers on the quality of this product, but we may prefer to listening to the actual experience of the neighborhood. So such a philosophy is adopted by explaining by case. So this class argues that we can understand the model with the help of cases. So on one hand, we can provide a similar case for a query. So given a query, we can generate a similar case for this query based on they are based on the closeness of the feature space of a neural network. So by checking whether or not a neural network generates a correct similar case, we can know if a neural network functions well. On the other hand, we can also provide a counterfactual case. Counterfactual case is so-called the closest possible case to yield a different outcome. So to construct a counterfactual case, so we need to change the input such that the model's prediction is also input. This is useful because we can compare the counterfactual case and the original case, such that we will know which part in the original case is dominant for the model's prediction. So lastly, in the first category, explaining by text. So this class generates a text description for the features. However, this class is only applicable for models with a language module. For example, the image captioning task. So a model comprises a CNN and a RN. CNN is in charge of generating features from the image, and RN is in charge of configure the corresponding words for the features with the help of attention module. So eventually, there will be a correspondence between an attention map and a word. So such kind of attention map can provide us an explanation for the model. Now we move to the second big category, ad hoc interpretable modeling. The first method is interpretable representation. The method in this class use regularization techniques to make the model have an interpretable representation. For example, decomposability. Traditionally, GAN doesn't have interpretability in the image generation. Although GAN is very successful in generating images, we do not know how the noise is encoding the generated images. The training of GAN involves two loss terms, generative loss and discriminative loss. Some people propose so-called info-GAN by adding an extra loss term called mutual information loss. So in the training of info-GAN, it maximizes the mutual information between the noise code and synthesized image, such that each code of the noise has a semantic concept. For example, in the right figure, by changing one code of the noise, the generated images become more and more rotated. So we can conclude that in the info-GAN, the image generation process is interpretable because we know the correspondence between the noise code and the generated images. So lastly is the model renovation. Model renovation method design interpretable machineries for a model. Our group proposed the so-called soft autoencoder for denoising. Traditionally, the wavelet shrinkage algorithm is good at denoising. It first does the wavelet transform, then do the soft thresholding operation, then do the inverse wavelet transform. So our idea is to map the wavelet shrinkage algorithm into an autoencoder. To make this mapping, in the encoder part, we replace the ReLU activation with the soft thresholding activation. And in the decoder part, we replace the ReLU activation with a linear activation. So the prototype the autoencoder on the top level is a learned wavelet shrinkage system. The second example is function decomposition. So this paper purposely designed the neural network architecture such that the output function of this network will have a simpler mathematical structure. If a neural network has a simpler mathematical structure, it is more interpretable. For example, in this case, if a network structure is in this way, it will be easier to construct the Selin's map for this network, because some Selin's map are based on the gradients. So the gradient calculation here is easier because the mathematical structure is simpler. We do not need to calculate the derivative a lot of times. So now let us compare the strengths and weaknesses of post-hoc interpretability and ad hoc interpretability. So post-hoc interpretability usually can have a better accuracy because we do not need to compromise the accuracy for a better interpretability. However, post-hoc interpretation is never completely faithful to the original model. What's worse is we do not know the difference. In contrast, the ad hoc interpretability introduces no biases because we construct a more interpretable model in the initial stage. So, however, we need to be careful about the trade-off between interpretability and expressibility. In the future, we hope to see the convergence of fuzzy logic and deep learning. We believe the synergy between the fuzzy logic and deep learning has a great potential. Fuzzy logic is interpretable, but it is rule-based. We know that getting rules is a tedious process requiring a lot of labors. But in contrast, a neural network is a data-driven method. It can ultimately learn the knowledge, but the knowledge is stored in the parameters in a distributed manner. So it seems that the fuzzy logic and neural network are complementary to each other. So they should be synergized together. So the fuzzy logic can provide a neural network a better interpretability, can hold the neural network accountable. We would like also to see the convergence of brain science and deep learning. Up to now, the human's brain is the most intelligent system. So we hope in the future the advances of brain science can help deep learning in terms of causal function design and bioplausible optimization and bioplausible architecture design. So now let me hand over this presentation to my advisor, Dr. Ji Wang.
Fenglei, I think, yeah, you did a great.
Sorry, I cannot hear you.
Can you hear me now?
Oh, yeah. Yes.
Okay. I said you did a nice presentation. Thank you. So anyway, so I will conclude this presentation talking about something related to our active collaboration with some investigators at FDA. And several weeks ago, we read this article in the Nature Medicine and talk about how medical AI devices are evaluated. So this is a very important topic. Next slide, Fenglei.
Okay.
The authors just did a survey and over past several years and over 100 FDA-approved medical devices are on market, and about 50% of them were approved in past year. And this small table just summarize application areas and some key characteristics. If the AI devices were evaluated on multiple sites or not, in out-of-date data or with carries high risk and others relatively low risk. So all these things, they just try to understand the current landscape. Next one. And these authors did a specific case study. So they just selected a typical network and for collapsed lung analysis. And they selected 3 data sets, one collected at Stanford University. So I just color it right. You can read how many 2D X-ray radiographs in the data set. So next one. So this green data set in Boston and by MIT, and a quite big data set, nearly 5 terabytes. Next one. And also the third data set checks the X-ray 8, and its blue data set is NIH data set, and also very well known. Next one. So here is key results. So the network is well defined. Just give you binary output. If the 2D X-ray radiograph contains collapsed lung or not, is a binary decision. And what they did, they trained the network on one data set. So performance. Then you test the trained network on the other data set. And so you do this for each of the 3 data sets. The overall finding is that and you can get a pretty good performance after training on the data set with the same distribution. But if you try to apply it, say in other institute, and then you will not get equally good performance. And very roughly, you get about 10% performance drop. And also in Boston data set, and they recognize there is a racial bias between white and black patients. So this is their key finding. So they made some recommendation. Next one. So they believe and to do good AI translation and monitoring and those things. So we should try best to use multiple clinical sites and also evaluate the results and the network in prospective studies. And the post-market surveillance is also very important. So they made all these things clear and certainly very valid point. Next one. So we are collaborating with Stony Brook University and UT Southwestern and RPI, FDA. We are trying to look into this. So we believe numerical simulation will have a good role to play. So if we use GAN network based on real data set, we can generate synthesized data set. For example, Stanford data set, we can generate simulated Stanford data set. Therefore, we have a red data set prime, green prime, blue prime. And the very first question, we would like to know if a simulated data set will do a similar thing to show if the out of distribution is a problem in these simulated data set. If so, we pretty much believe so. So we can use more simulation tool to help AI device evaluation. So overall, this is something we are actively exploring. And Fenglei just mentioned the interpretability of neural network. So we feel maybe there also a interpretability problem of big data. And there are several very important questions. Some already partially answered, some remain unanswered. For example, when we have a big data set, and we want to know if this big data set is out of distribution relative to some training data set. And if the data set contains, say, racial bias, gender bias, and so on, And so if we know the data set is out of distribution, then we would be very much alert about potential performance drop. And the adversary attack is another issue. So we think interpretability of big data could be a potential research topic. We need to spend some effort. And once we have a big data, and we want to know distribution, and this is not easy when the dimensionality is high. So some general question like, does a big data allow a sparse representation? Okay. Also, does a big data allows a diverse representation? So don't want a lot of data give you redundant information. And also, how do you detect the big data is out of distribution? So a lot of interesting questions, and we look forward to continuing collaboration with FDI. Okay. So this is